Okay, great. So the big focus today is the midterm review, but before we get to that, I just want to switch to mentioning that the inverse transform technique that we did last time for continuous distributions also applies to discrete distributions. We've chatted about this already, so I just want to quickly go through a couple of those slides to give you a more formal idea of what I mean by that, because this is an important topic and a topic that I might ask about on the midterm. So last time we talked about the inverse transform technique and how we can go through all these steps. So you can start with a piecewise PDF like this one for a triangular distribution and end up down with something that through multiple steps here, you end up getting to a CDF that looks like this one for the triangular distribution, a nice S-shaped CDF. And then from there, you end up taking the inverse of that CDF. So you do an inverse by pieces. So you kind of have to figure out which range of the CDF corresponds to which range of the inverse CDF. Then you can do that by plugging in values. So if you plug in A into this one, you'll find out the one end of the inverse CDF range. If you plug in C into this one, you'll find the other range or the other end of that interval. And then that gives you this interval here. And then if you plug in C into this piece and then B into this piece down here, that'll give you this interval down here. And then once you've got those two, then you can invert each one of these individual pieces separately, independent of each other, and just apply these ranges to it. And that ends up giving us the inverse CDF that we see way down here. With the caveat for this particular one that you have to make sure that when you take square roots, that you are sure to assign the pluses and minuses so that the ranges are in the right range for the random variable. This random variable goes between A and B, so we better make sure that it's generating numbers only between A and B. And if we choose a plus for this one and a minus for that one, then we end up making that work for us. So that's how we do it for a continuous random variable. And we would then could go into Excel and we could put in uniform random numbers between 0 and 1 into that funny function that we just built up there. And we could then take the histogram of the results like you did in the homework, and you would get a nice triangular distribution just like this. In Arena, they've done a lot of the work for us because the triangular distribution is so widely used, because it's very often somebody will say, I don't really want anything less than this or more than this, but I want things to on average be around this thing. And so they don't tell you about the variance or whatever, but they give you bounds and they give you a mode, really. They might say an average, but what they really mean is a mode. And that's a triangular distribution. And so Arena already has that implemented for you. But imagine if they didn't. Well, if they didn't, you could go back and implement this ugly thing in Arena. So what would that look like? Well, so you can go in and you can create a little assignment block like this one in Arena, and you can assign a random variable R to RA, and RA is Arena's shorthand for uniform random number between 0 and 1. And then you can implement this ugly formula that I'll zoom in here, which uses that random draw from R there. So in this ugly formula that I put down here, then you basically can assign to this thing I called tria sample or tria sample, this expression here, which basically says if R is less than a critical value, it applies one formula, or if R is greater than a particular value, it applies another formula. And so that is, in theory, how you could take these ugly piecewise formulas and actually implement them in Arena and have Arena draw from a random variate distribution that it doesn't already have pre-built in for you. If you actually look up, you can ask Arena for the help for TRIA, and it'll give you some details on how TRIA is implemented internally, and you'll find out it basically is implemented very similar to this, but they just do all the stuff behind the scenes for you. So that's, for the continuous ones. And if you had other continuous random variables, before you go through all this mess of inverting and whatever, you can just Google for what's the quantile function for a Rayleigh distribution or something like that, or what's the inverse CDF. And you might find that someone's already built up all of these things for you, and that allows you to very quickly generate random variate generators. You just have to code up these quantile functions inside Arena or Excel, and you can sample from any random distribution you want, as long as you've got that quantile function. And that's how we do it for the continuous ones. So are there any questions about that before I cover what I wanted to make sure we cover for the discrete random variables, which is it's fundamentally the same process, but the mechanics look a little different? Or is that pretty clear? That's just exactly what you've been doing in your homework D2. All right, let's roll on, and then we can spend most of the time then on the review. So I mentioned that I could also give you a discrete random variables probability mass function like this one. And if I wanted you to build a random variate generator for this random variable, just like in the continuous case, you would need to solve for the CDF. And so in a probability mass function, it's pretty easy. If I just give you numbers to solve for the CDF, you just kind of accumulate those numbers. And so the first outcome, you pull that straight down. The second outcome is just the first outcome's probability plus the second outcome's probability, and that becomes 0.7 there. And then to get the last outcome here, again, I just add its probability mass to the accumulated value, and I get 1. So it always ends in 1.0, as any good CDF should. And so you could plot that thing out. So we've got our outcomes, we've got our CDFs, and then we need to invert that CDF in the discrete case. And so we could, if you notice, all I did is if you were to draw a diagonal line here, so if I were to, maybe I'll use the magic of Zoom here, and if I were to draw so bring this in, or to draw what I'm going to try to get a diagonal line from up through to about here. So I don't know how diagonal this will end up being, but if I go to the next slide, that line should stay there. All right, let's get rid of that. All right, so now if I go to the next slide, I hope you can see now that line is there, I'm just folding it along that diagonal line. That's what taking an inverse is. And when you fold it along that diagonal line, you're just taking what used to be the outcomes variable on the horizontal axis, and I'm putting it on the vertical axis. And you're taking what used to be the cumulative distribution that was on the vertical axis and putting it on the horizontal axis. And so that's all that I did there graphically to invert that. And then that allows me to then draw a random number. And so on a midterm, I could give you the random number. And then I would ask you to say, calculate what is the corresponding outcome that would come from this random number if you were to generate a random variate generator for this random variable. So I could do that for continuous or discrete. And so if you had the inverse CDF, then you just plug into this inverse CDF. And so for a discrete one, then it's a little, so for the continuous one, you'd have a nice smooth line going through here, and you'd find out exactly where that hit. For the discrete one, you basically choose the outcome where the CDF is kind of brackets the random number that you drew. And so I drew a 0.54, and I can see that my CDF has, is 0.2 at one outcome and 0.7 at another outcome. And so I am going to choose the lower of those two outcomes. So I'm going to, if I were to, and graphically, it just looks good graphically here. You just go up to the dashed line that's between them, and then you kick it over just like I would in the continuous case. So that I showed graphically, we can also write out a little more mathematically, and I think it becomes a little more clear exactly what the process is. So let me clear this annotation. Okay. All right, so so mathematically, what we're seeing here is that for this random variate, for this random variable, discrete random variable, my CDF down here, 0.2, 0.7, 0.1, this CDF effectively gives me boundaries of the random number that I draw and how it maps to the outcomes of this random variable. And so this 0.2 basically means anything between 0 and 0.2 is going to get an outcome of 1. This 0.7 basically means anything between 0.2 and 0.7 is going to get an outcome of 2. This 1.0 means anything between 0.7 and 1.0 is going to get an outcome of 3. And that's all that I've just written out down here. And so, So if I were to give you a raw probability mass function, if you could then calculate the cumulative distribution function, and then if I were to give you a random number, 0.25, then you should be able to look at this and say, okay, 0.25, that is in between these two outcomes. And so I am going to then pick this outcome up here. If I give you 0.15, I can say 0.15 is to the left of the leftmost outcome. So it's going to be the leftmost outcome, and so on. That's how you would do it by hand. In ARENA, they have implemented for us a nice function called disc, where disc stands for discrete. And in disc, you basically load up the inverse CDF into the arguments. And so for disc, the first argument is the 0.2 right here. The second argument is the outcome right here. The next argument is the 0.7 here. And then the argument that pairs with it is the outcome up here. So disc just allows you to take the inverse CDF that you solved for and just load it right up into ARENA. A lot of people, when they look at this, get these confused. And so on a test, I could ask you about the syntax of disc. And a lot of people like to do outcome and then probability. And a lot of times they don't do cumulative probability, they do probability mass. So it's, it's tempting to want to say, to load up disc with the probability mass function. It's tempting to want to say this should be 1, 0.2, 2, 0.5, 3, 0.3. That's the tempting way to load up disc. But traditionally, and there are reasons for this, but traditionally you don't use the probability mass function here. They want to kind of make sure that you've done your math correctly, and you use the probability, the cumulative distribution function. And that means that if you don't end on 1.0, and if you don't start on a number that makes it so that all of these first arguments are increasing, when you hit run in ARENA, it will then throw up an error to say that your disc function here doesn't have, like, monotonically increasing probabilities. It might say that, or it might tell you that your probability doesn't end in 1. So it can then throw up these errors to say that you didn't give me a valid cumulative distribution function. So just remember, with disc, it is effectively encoding the inverse CDF, which means it's going to be CDF, outcome, CDF, outcome, all the way down through it. And it will then do this roulette wheel sort of thing, where it is going to roll a random number for you between 0 and 1, and then it will do this process, which you should also know how to manually do, but it's doing this for you, this kind of dartboard process. That's what's going on behind the scenes. Okay. So there are special, so before I go on to the cases where, so this is the case where I've got a probability mass function I've specified in numbers, but I can also give you a probability mass function specified as a formula. And so there are special cases that we can handle in that particular setting. But are there questions about this? About understanding what's going on down here with the disk, for example, or any of this stuff here? Is this clear from just PMF to CDF and then doing the discrete version of what we did in the continuous case? Okay. All right, so it is also possible that you are just given a bunch of data. So, so this isn't something we do on a midterm, but this is definitely something you'll do after the midterm when you start taking data on systems that you're going to model. And so if I just give you samples of data, so these are inter-arrival times. So just a bunch of inter-arrival times for of people arriving at a bank. And so sometimes they're 10 seconds, sometimes they're 3.3 seconds or whatever. Just have a bunch of data. And these data could be continuous or could be discrete. And I don't know what the distribution function is, and they're not fitting any of the known ones that I can find. It just doesn't look exponential, it's kind of bimodal, and I just am not confident in fitting something with this. So in that case, you can do you can generate what's called an empirical cumulative distribution function. And so what you do is you sort all of your data, just like you were doing in the Kolmogorov-Smirnov test. In fact, this is very closely related to the KS test. So you sort all of your data, and then you associate each point in the data with its ranking divided by the total number of data points. So this is a particular data point that I found, 10 seconds, and 10 seconds might be 5th in the ranking out of 30. So then I would make this 5 divided by 30 over here. So you could pair each outcome in its sorted order with its ranked in the sorted order. And that gives you what's called a cumulative distribution function. And so if I were to plot, you know, if I were to tabulate all of my outcomes here in the top row, and I can then put all of those pairings that I paired them with in the bottom row here. And what we're seeing is what we're actually doing is approximating this data set that we gathered as if it was a discrete random variable that only took these outcomes, the outcomes that you observed. And each outcome only occurred once. So the probability mass for each one of them is just 1 divided by the total number of outcomes. And so that's kind of what we're approximating this unknown data set by. And now that we've approximated it as a discrete random variable, we can then just sample from it as if it's a discrete random variable. And so we can use disc just like we did with a real discrete random variable. Just now, instead of having 3 outcomes, we might have 30 outcomes or 3,000 outcomes. And it will then match you know, those outcomes according to how frequently they occur. So here's an example where I took a bunch of data, like up here, and I sort that data and I plot that data against its normalized rank in the sort order, and it looks just like a discrete CDF. Because it looks like a discrete CDF, if I want to sample in a way that's statistically consistent with the data that I gathered from the real world, I just draw a random number between 0 and 1, and then I find out where it hits this approximated CDF. And that's the same thing that we would do for a standard discrete random variable. And so I can implement that in disk by just basically making each, you know, 1 over n, 2 over n, 3 over n, all the way up to n over n 1.0, and pair each one of them to the sorted outcomes. So again, this is a way I just implement a discrete CDF or discrete inverse CDF in ARENA. The downside with this approach is that if I take histograms of the outcomes that come out of ARENA, then my histograms are going to only show me outcomes that were in my original data set. So my original data set was probably not discrete, but I approximated it as if it was discrete. And when I implement it this way, if I only have a small number of outcomes, then I'm going to get an outcome out of ARENA that's going to look very weird, and that even though, you know, like if my outcomes from the real world were 0.4, 0.95, 0.25, you'd expect occasionally you to get something like a 0.5 in there. But here, 0.5 will never occur. It only will simulate things that we've actually seen in the data before. Now, if I saw 0.4 a lot, then it would end up showing 0.4 a lot in the simulated outcomes. But there's nothing will ever show up in between. And so that's something that's kind of a little weird about that. And so there is a way that we can fix that. And we can take our approximated discrete random variable here, and we can just interpolate between the points to sort of say, we know that between 0.4 and 0.25, that range is pretty common. And so we're going to make everything in between them also pretty common. But we know that over at 0.8, it's not as common. And so our outcomes there are not going to be as common. And the way we do that is we take our approximated discrete CDF and we just create these interpolated lines where we just say, okay, from 0 up, we go to the first point, and then we just draw these lines here. And then now we have an approximated continuous CDF. And from there, we can then sample from this continuous CDF, and we will get everything in the range from the lowest outcome we've seen to the highest outcome we've seen. It still creates a problem for outcomes maybe outside of the ranges we've seen. And actually, in I think this particular case, it will give us outcomes less than the outcomes we've seen, but it doesn't ever give us outcomes greater than the ones that we've seen. So it isn't perfect, but you're at least getting intermediate outcomes, intermediate to the ones that you've actually seen in the data. And if we were to now take a histogram, then all of these lines in the CDF turn into piecewise uniform random variables here. So again, you should get used to, whenever you see a line in a CDF, in your head, think if I were to histogram that, then I would end up getting flat portions in my approximated probability mass function in my histogram. So that's what they were seeing here. The slope of this line corresponds to the density in this histogram here. And in ARENA, they give us this nice cont, and it has exactly the same syntax as the disk, but you can also throw in front of it what you want the minimum value to be. And so you can kind of pin the minimum value. You're still stuck, your maximum value is whatever the maximum value was in your data set, but you can throw in an additional minimum value that you associate 0 probability with. And that's where the probability density will start rising. So that will be the low end of your range. So otherwise it's identical to disk. It's just called cont, and it does this interpolation for you. It just creates this continuous CDF for you and then draws a random number from it. All right, so that's one special case I wanted to throw at you, is if you get a data set, you can convert it to a discrete random variable, and then you can take that discrete random variable and approximate it with a continuous random variable, and hopefully it'll be closer to the data that you've actually got. The last case I think that I wanted to show you here is the one where you have a formula. So like the geometric distribution. So the geometric distribution, let's recall, you should know that the geometric distribution is the discrete analog of the exponential distribution. It represents the number of coin flips until you get one outcome that you're looking for. So we are interested in the distribution of number of coin flips until you get a heads. So if a heads is kind of your failure event, then sometimes you'll get a heads immediately, but other times you might get tail, tail, tail. It might take 6 flips to get your first heads. And so the distribution of that is the geometric distribution. So it's the discrete analog of an exponential. You think of an exponential as a waiting time to a failure. This is the discrete waiting time, the number of counts until a failure. And just like with an exponential, we have a formula for its the way its probability is distributed. And so with a geometric distribution, we have a formula. We have a probability mass function in a formula here. And so because of that, then we also have a formula then for the CDF, and it should be not surprising that it looks similar to an exponential CDF. And so when we do the inverse transform sampling, now rather than having to sort of build up this kind of raw number CDF that we'd have to load into a disk function, we can use a little bit of math, and we can say that whatever random number I draw, it's going to be between 2 levels of my CDF. And so you can write a nice little inequality here that says that there is some outcome level K and some outcome level K plus 1 that have cumulative probabilities that will sandwich my random variable, my random number that I drew. And so that's all that I'm showing here, is that this here is the cumulative distribution function for some hypothetical outcome K. And this is the cumulative distribution function for the outcome that is the next up from K. And so this double inequality I can solve, and I will get a function that maps from any R value between 0 and 1 to a particular K value that meets this condition. And that allows me to have a nice clean function, so I don't have to use disk in order to simulate a geometric distribution. So if you do a little bit of math, you apply some logarithms, you end up turning the inequality we saw in the previous slide into this thing. And if you think about it, then this thing right here is equivalent to just saying that the outcome K is going to be the ceiling. That's what this funny bracket is here. The ceiling, that means the next integer that is higher than, so this, you evaluate this logarithm divided by this other logarithm, and then that gives you a number, a real number, and then you take the next highest integer from that number. And so that's what this ceiling operator here. So the smallest whole number that is bigger than what's inside here. And then that there becomes the outcome that we end up drawing. So now this is a simple formula that you could simulate in Microsoft Excel. You draw a bunch of these random numbers in one column, and then you put this formula in the other column, and then now you can sample from a geometric distribution. And notice, if you remember the formula for an exponential generator, this is very similar to that. And so, so that is another way that you can solve for these inverse transforms. And if you're just interested in how to implement that in Arena, there's the formula for how to implement in Arena. I'm not going to test you over that, but just if you want this in your notes, the way you can implement this kind of ceiling operator is you can use this function and int in Arena, and then you have to add 0.5 to the thing in between, and then that will end up giving you the equivalent of a ceiling operator. So, so this is at least possible, even though Arena does not have a geometric distribution built in. You can't easily implement this formula in Arena, so that effectively allows Arena to simulate a geometric distribution. All right, so that's all of the new content that I wanted to cover before we talk about the midterm. Are there questions there about those different categories of how we make use of discrete random variables and the inverse transform technique? Okay. All right, well, we can, if there are other questions, we can bring them up as we go through here. So basically today, I'm happy to just take questions. I can actually flip to a whiteboard. We can do things there, or I can just show you slides that hopefully will inspire questions that will pop up as we go. Just, a couple of administrative things. So we're doing this midterm review today. In the next lecture period, which will be Tuesday, we will have the midterm. Now, what I mean by that is because this is a strange, COVID times. In the before times, you would have come in and spent 75 minutes in class doing the midterm. Now, what's going to happen is on Tuesday, there is a midterm that you have to take that Respondus Lockdown Browser compliance test, but that will unlock the midterm unit. So several people have already taken that. Make sure you do that. That'll unlock the midterm unit, which also has a bunch of good study materials. And that the midterm will be in there. So on Tuesday, at early morning Tuesday, like midnight Tuesday, so overnight Monday, then that Arizona time, that will midterm will become available. You can then start it anytime you want during that 24-hour period. So you will have all of Tuesday Arizona time to start the midterm. Once you start it, I'm going to give you, I normally give you 75 minutes. And if you have DRC accommodations, I will deal with those. I will expand those as needed. But then if based on the 75-minute period, I'm actually going to give you 90 minutes to deal with any technical problems you might have. So if there are any sort of technical difficulties or whatever, it won't eat into the 75 minutes the midterm is designed for. And then you'll then have that 75 minutes to complete the midterm with Respondus Lockdown Browser with the monitor. I'm not a huge fan of Respondus Lockdown Browser with the monitor, but it's the most convenient way for us to administer these midterms. And so you'll take that, and then you'll complete it, and then it'll be done. And then after the 24-hour period, a solution set will become made available. And then the next week, so Thursday of the next week, so after what would normally be fall break, then we can repeat the process. And so that Thursday, there won't be a lecture. It'll be just like the Tuesday, and a midterm retake, which will be different than the midterm. Same length, similar content, similar difficulty. So basically I design these two things by setting them next to each other. And whenever I generate a question for one, I try to come up with a pairing question for the other. And then you'll have a chance to do that one again. And I will take the maximum of those two scores. If you don't want to take the midterm on Tuesday, you can just wait and take it on the retake. If you don't want to take the retake, you can skip the retake and just be happy with your score on Tuesday. Or you can make the decision in between. You can take the Tuesday midterm, see what your score is, see the solution set, recalibrate, and then decide, okay, I'd like to take the retake. So neither of those days will have lectures. So that way everybody has got a 75-minute period of the day where they are free to take the midterm for sure. And then, but if you don't want to take it, then you can take it anytime that day. So that's how things will run in this COVID time. It's a little different than the before times, and that's why You know, the text here is a little different because it's all going to be auto graded. You will have your score immediately, and I should have a solution set available nearly immediately as well. And so you'll have at least a week to review the solution set and decide whether you want to take the retake. So that's how things are structured. Are there questions about that? I know that's not necessarily the most conventional way we do things in IEE classes, but that's how I've been doing things the last couple semesters here, and I've been happy with the results. So, okay. As just a heads up, because of the final exam week being so weird with this innovation quarter thing, and we have to do all the final exam assessments in the last week of classes, I am planning something a little bit different that won't necessarily be a retake, but it will still allow you for this kind of second chance. And I haven't totally committed to that idea yet, and I won't tell you about it yet because I don't want to confuse anybody about the midterm plans. But in the final exam, if we don't have a retake, we will have something that is similar to a retake that you might even like better than a retake. So I'll tell you about details about that after the midterm so we don't confuse you for these midterm protocol here. All right, so that's the details there. Lots of midterm resources. Again, take that compliance check. It'll unlock that midterm module. I think there's sample midterms for at least 4 years, maybe 5 years, multiple, in some cases, multiple versions per year. There's the ICA, the ICF that was due today. Well, there's now an ICAF practice that's just the exact same thing as ICAF, but it just doesn't count for credit. So you can take those things to kind of have, additional challenges to work through. Of course, there's the videos that are out there, the lectures. And then there's the book, and then you can also go through the book. So lots and lots of resources out there. If you have any questions, then feel free to let us know. But if you're looking for practice and things like that, lots of practice has already been out there. You are allowed, I think I've given you two-sided handwritten formula sheets. At least that's what I say here. For some reason in my head, I thought it was one. Pretty sure it's one actually. So let's, I'm gonna cross that out because unless it says differently on the midterm, on the Canvas page, and I will double check this, I am almost 100% positive that this is actually one two-sided. So this is supposed to be a one here. And I'll double check that for sure. But, and because this will be on the lockdown browser, you'll have to show it to the monitor. Maybe that's actually right. No, I'm sure it's one. It's either one two-sided or two one-sided. So either one of those. You can type it, but I don't want any copy and pasted work. So I don't just want you to copy something out of the book or copy something out of my notes and just paste them in. I want you to either handwrite them or hand type them. So you kind of are forced to go through that process, but then you can have those formula sheets. And then this is stuff from the last time. There won't be an A and B version because it's all graded online. There'll be randomization involved in there to make it so that if one person takes it, the other person might have a slightly different experience, but all the questions are effectively the same. So we don't, so this is just a kind of old text from the previous semester. So let's clear that. Like I said, you can see sample midterms online for example formats, but basically when I design this thing, I start out and I want to give a bunch of what are, they're all going to be multiple choice questions, or there'll be fill in the blank. There'll all be things that Canvas can auto grade, but the motivation for how I build them is that the first, say, 10 to 13 problems are going to be concept related questions. So I might show you a discrete event system simulation table. You have to fill in cells. I might ask you for, well, what would be the right statistical test in this particular case? What would be the right distribution in this particular case? Match up this distribution with this thing that you would likely use to model with distribution, and those sorts of things. So a lot of multiple choice. Then you will have to do some numerical things. So you might have to execute a DES by hand and then tell me, so because it'll be multiple choice, it'll be after you execute it by hand, there'll be a calculation that will then be filled in that multiple choice. You might have to generate a sequence of pseudo-random numbers or use a statistical test like a chi-squared test on a sequence that I give you. And then you're definitely going to have at least one design problem where I'll give you a density function or a CDF, and you'll have to then generate random numbers based on that. So I'll give you the random numbers, and then you generate random variates with those random numbers. So I'll say, here's a couple of random numbers, 0.4 and 0.7. What would be the two corresponding random variates if you generated the random variate generator? And so you'll have to go through that process. So because of that, I'm also allowing you to have some scratch paper available. So it'll say that in the Canvas version, but you can have, I think, two initially blank sheets of scratch paper that you can have sitting there with you, so that if you need to work things out, you can. So you have to show me that they're blank ahead of time, and then you can work things out and answer that. So that's the basic format here. Any questions about the format? Okay. All right. Well, so from here on out, as you know, we can spend the rest of the 40 minutes or so, right? I've got slides here, so I've got slides that are about kind of feedback from the first couple of homeworks, pitfalls from the homeworks. I've got also my kind of greatest hits from the lectures, and if and so I can say, well, go back to the first lecture. What are the things that I think were important? So I can run through those, and you can then holler whenever you see something that you'd like to know more about. Or right now, if you've got questions that are lingering, like, man, I still don't really understand how to do X or why this was the right answer to that, then this would be a great time for those things too. So do you have anything that you'd like me to talk about now? Or do you just want me to drone on with the prepared stuff? Anybody? Okay. Yeah, all right. So prepared stuff. I go back, look at your homeworks. The homeworks are good practice. I would definitely make sure that you're comfortable with all the lingo, all of the, what is an entity? What is an activity? Can I name these things? You will definitely be asked, here, we're going to model an airport. What would most likely be how, the entities in this particular section of the airport? What would most likely be the resources in this particular thing that we're modeling in the airport? So know about, what is an entity? What is a resource? How, what is the difference between an event, somebody arriving, an activity, someone getting their luggage checked? So all of this sort of stuff that we went over in that, that asked you to sort of manually kind of build these kind of basic models, make sure you know about those. Know the difference between states and state variables. We can have a state variable like customer status, and the states of that could be something like tired and awake. So they're two discrete states, tired and awake. They aren't necessarily numbers, but we still view them as states. Again, the difference between events, activities, delays, those are all really important. When you're executing, make sure you know how to execute a DES by hand. Make sure you don't schedule events too soon. This is like the #1 problem that people sort of have when they do these, is that they're tempted to schedule multiple arrivals in a row because they anticipate when those next arrivals are going to happen. And since they already know in their head when they're going to happen, then they put them on the future event list because they say, well, I'm just going to take a shortcut. A simulator, a computer can't make those shortcuts. It can only do one thing at a time. And so it only is able to schedule the things it knows absolutely need to be scheduled right at this instant. So don't schedule too many things too soon. Whenever you start an activity, you're going to start an activity because an event happened. And whenever you start an activity, you must schedule the end of that activity. And activities always come with start events that kick them off and end events that they generate. So if you're in your head, if you thought, I just started an activity, you should immediately think, I need to schedule the end of this activity. So that's kind of a mental heuristic to know when you're supposed to schedule these things. Yeah, so that's just sort of all kind of saying with that. So, so that's kind of my big homework or my feedback from homework B1. Are there any questions about the differences between, resources, activities, events, delays, when to schedule these things? Okay. All right, other things. So then moving into homework C2, definitely know how to generate random numbers. So I definitely could ask you to generate a couple of random numbers. I might give you an LCG. And so I'm not gonna ask you to do the middle square method or anything like that, but I definitely could say, generate 5 numbers in sequence, starting with this seed of a linear congruential generator with this multiplier, this increment, and yeah, so that a bit. So I give you the seed, multiplier, and increment, and then you would have to roll forward with the generating, say, 5 random numbers. Know that the seed that I give you is not one of the 5. So the seed that I give you, don't divide the seed by the modulus and say that's my first random number. That seed goes into the LCG, and then the first number that it produces, then that divided by the modulus is going to give you the first random number. So that's kind of a common thing there. So that's what I'm saying here. The seed should not be used to generate that random number. There's, on a midterm, when everybody's stressed out, there's a bunch of easy mistakes that are made. And I see this time and time again every semester, stuff that you wouldn't expect to happen at this level, but they do. Be careful about place value issues. And so, like, especially when we're talking about, if I'm doing a chi-squared test and you need to make sure, like I give you a bunch of outcomes and you need to count how many outcomes are between 0 and 0.25. Well, then you need to know to yourself that the difference between 0.25 and 0.127, like I think a lot of students when they're stressed out, when they see 0.127 in their heads, they think 127, and 127 is greater than 0.25 because 127 is greater than 25. But you just have to back up and take a breath and say, no, remember my place value, 0.25 is greater than 0.127. And again, this sounds like, it sounds like something silly that I shouldn't, be taking time to remind you of, but these errors happen every semester, is that people put things in the wrong bin because they just, in their heads are moving so quickly and they see 127, they don't see 0.127. So be really careful with that. Likewise, when you're dividing things, when you're generating random numbers, if you divide something by 1,000, remember however many leading zeros you need. It happens all the time where I'll say a modulus of 1,000, and it just so happens the number you generate is 71. And so people then look for, they end up putting 0.71. They forget that, oh, okay, I've got that extra 0 that I need to put in there. So be really careful about that stuff. Know how to use the tables for the chi-squared test and the KS test. So the degrees of freedom for the KS test are the number of samples. This is different than the degrees of freedom for the chi-squared test, which is the number of bins minus 1. So that's kind of an important thing. For both the chi-squared test and the KS test, you don't divide the level of significance by 2 or anything like that. You actually take the level of significance exactly as it is. So that's how you find these critical values. And then in your head, I might ask you a conceptual question about what the heck these statistics mean, chi-squared and KS. And just remember, both the chi-squared and the KS statistic are distances from the assumed or null hypothesis. And so the bigger they are, then the more unlikely the data came from the assumed distribution. So, so bigger is worse. So that's something that you maybe can think about in your head. How do I use these thresholds? And this threshold represents the largest distance you can get before you say it is too unlikely for this to have occurred if the null hypothesis was true. And the null hypothesis for this particular case is uniformity. And sort of we want uniformity, so the null is not like a bad thing. We want to detect if this thing differs from what we want, and that's what the test is doing. So with that in mind, remember that I could phrase things asking for a little bit of interpretation. So know what the null hypothesis is for these tests. So for the chi-squared and the ks, the null hypothesis is that the random numbers came from a uniform distribution. So if you reject the null, you're saying that these random numbers came from a random number generator, which is not a good approximator for uniformity. So being able to interpret these things, know that, because I could ask you, say you get we reject the hypothesis. Does this mean A, B, or C? And then, these would be different cases for referring to the interpretation relative to uniformity. Yes, you will. There's a question in the chat. Will we provide tables? You will get chi-squared and ks tables. And I might even throw in some other tables just for fun. Might give you t tables and z tables. I definitely will give you z tables because you might need the z tables for the runs test. So yeah, you'll get all of the statistical tables that you would normally find in the back of the book. I will give that to you right on the first page of the exam. So there will be right at the candidate top, you'll get all the questions at once. So, and you'll be able to scroll through them. And at the top of that, then I'll have those tables up there as if they were like the back of the first page of the paper exam. Okay. Questions about any of that stuff? Random number generation, testing random numbers, or about that homework? All right, then random variate generation. This is the homework that was technically due already, but you've got until Saturday night to do it. And it's I think a strict Saturday night. So make sure you get it in Saturday, not like early Sunday morning. And so with that homework D2, these piecewise functions are tricky to deal with. If use the properties of the CDF to tell you if you've done something wrong. If things aren't lining up just right, then in your CDF has got to start at 0 and it's got to end at 1. If it's not ending at 1, like this CDF, then you've done something wrong. And if it is decreasing at any point, you've also done something wrong. So, if you find that as you're evaluating this, that the numbers are getting larger and larger and larger, but suddenly you hit another piece where once you hit this, this end of the interval, it gets a lot smaller, then you probably haven't carried over something. You haven't probably used your limits of integration correctly. And so I guess the two big problems that I've seen in homework D2 is one, when you're calculating, let's say, this third row, people often forget two things. They first forget to include the contribution from the second row. So basically, if you were to evaluate the CDF of the second row that you've just solved for at this endpoint here, that needs to be included in the beginning of the CDF for this third row, because you need to start where the second row left off. The other thing people forget to do is when you take the integral of this point here, or this density here, you have to take that integral with limits that start wherever we say that range starts. And so you don't just take the antiderivative, 1.5x. You have to think this is, oh no, this is 1.5x minus 1.5 times 1.5, because that's where this is here. So that extra, that minus, I need in there, and it adds to that constant that pushes this thing up, and that helps keep things so that at the end of this range, it'll be at the 1.0 that we expect. And then if you've done everything right, then there should be 1 here at the end. So, just, yeah, keep in mind your properties of a CDF to evaluate if you've done the integration correctly. So that's all I'm saying here. I'm not going to go through this again, but I'm just kind of stepping through that process so that you're free to look at these slides. But you handle the first row, and then you bring down both the first row and the second row, where the first row, we're taking the integral all the way up to the end of the interval. And then we're then just adding on to it the second row, starting from the end of the first interval, going up to x, because for this point, we're stuck right in the middle of the second row. And then you can do those integrals, and notice again this 0.5 here. That's an important thing, and that when I take the integral, that 0.5 shows up here. So not only do I have a constant that came from the first row, I also have an additional constant that comes from the limits of integration in the second row. And so you have to, keep your limits of integration in mind, and then you can build this thing up, and eventually you should get a nice CDF with all the right constants so that it is non-decreasing, starts at 0, and ends at 1. All right, any questions about going from the PDF to the CDF for a continuous random variable? Okay. And then inversion, that's another one that's hard for people, and understandably so. This is, it's abstract to get this stuff in mind, but give you a CDF like this. Remember, the CDF is mapping the entire real line, that's X. Remember, that's a measure space, entire real line, to us in a small interval, 0 to 1. And so these intervals of the real line each need to be mapped to whatever interval the CDF maps them to from 0 to 1. And the simplest way to do that is just to evaluate them at the boundaries. And it turns out that we really only need to worry about this for pieces whose probability density, that was on the previous slide, are non-zero. And so if we were to cut back to that previous slide, we know that these two middle ones have a probability density that is not 0. The other way to look at that is if the cumulative density is constant, we're not going to need to worry about that when we invert them. Because if you think about the kind of graphical perspective, if it's a constant CDF, when that number comes in, it's not even going to hit that horizontal line. So that's why we're only focusing on these middle ones here. So I just need to plug in the bounds, my X bounds, into the CDF, and that'll give me my R bounds. And those will be the bounds that I use for the inverse CDF. And that's all that I'm just saying here. So I've got my CDF. This is the only portions that I care about. And for the top piece here, if I plug in 0.5 into here and 1.5 into here, what I'll find is as I'm going from 0.5 to 1.5, I end up going in an R range from 0 to 0.25. Now, it might just be that the ranges will be reversed, where the low number here will be the high number in the R range. And don't be freaked out by that. That happens all the time. All you really care about is the length of the range. And so then that tells you that for this piece, I know that in my inverse CDF, it'll correspond to this range of the R. You have to update those R ranges. It's a big deal. All right, and then once you've done that, then you can just solve the inverse. And this is back to like high school algebra, taking inverses of functions. And so you set R equal to this thing up top here, and then you solve for X. And that gives you a function, and then there is the range there. And then I'm just going to go through it, quickly here, but that's what you do the same thing for the second one. So I'm not going to step through that, but I've got all the steps there in case you want to review that. And then that gives you this. And so on a midterm, I might now ask, all right, here's a random number, it's 0.5. What random variate comes out of your random variate generator? Well, if you didn't set up your ranges properly, you wouldn't know that 0.5 belongs down here in this second row. And then if you did set it up right, you would evaluate in the second row, okay, 0.5 plus 0.2, that's 2.5 divided by 1.5. Do that on my calculator. And you can have a calculator, you just have to show it, but I don't want to, when I review these videos, I don't want to catch you like scrolling through your calculator for extra notes or anything like that. But yep, go ahead.
Sorry, could you just explain again how you figure out what ranges are going to be based off of the X ranges?
Yes, sure. So right on this page here, I've got everything kind of summarized. And so this up here is the CDF. And these are the CDF ranges. And so if you're okay with those, all you do is for the boundaries of the CDF ranges, you plug them into the CDF to see what value of the CDFs come out. So if I were to take, so I'll bring my little spotlight down here, which, see, yep, okay, great. So if I were to take 0.25 times 0.5 minus 0.125, then I find out that so I'll put this over here. So I find out that 0.25 times 0.5 minus 0.125 gives me 0. So that is where I got that 0 down there. So if I then go and plug in the other value, 1.5 here, so I'm just going to go back through and I'll do 1.5. So 0.25 times 1.5 minus 0.125 gives me 0.25. Well, there's where that 0.25 came from. And in the magic of all this, how this works, then for purely continuous random variables, it should be the case that when I evaluate that interval boundary in the next piece, they should kind of agree on the range for these random, for this R. So if I go down here and I do now 1.5, I'm just going to take the CDF 1.5 times, and then I'm going to take this 1.5 in the range, 1.5 minus 2, I again get 0.25, which is where I got there. And then if I then plug in the 2 instead, 1.5 times 2 minus 2, that gives me the 1, which is where I got right there. Does that make sense? Does that help?
It does. Thank you so much.
Mm-hmm. Okay. So, and this is, I'm just going over those sanity checks. And so one other nice sanity check you can do is, did I do this right? You know, before I submit my answer, did I get this inverse right? If you got the inverse right, you should be able to go from a CDF to the inverse and back, and everything will agree. What do I mean by that? What I mean by that is if you evaluate the inverse CDF at 0 and it gives you a 0.5, then when I evaluate the CDF at 0.5, it should give me the 0 back. If I evaluate the inverse at 0.25 and it gives me a 1.5, if I go back to the CDF and evaluate 1.5, it should give me the 0.25 back. So what I like to do when I design these homework problems and all that, just to make sure that I did everything right, is I evaluate all of the boundaries for the inverse, and then I then go back to the CDF and reevaluate whatever I got out of the inverse into the CDF to see if I get the original value back again. And if I can do that for all of my boundaries and they all check, then I'm pretty confident that everything in between the boundaries is also going to check. Okay. And then be careful about your square roots. I've mentioned this before. If I give you a CDF that's got a square in it, you're going to have to take a square root. And for this particular CDF, basically, the idea here is that this CDF is flat and then rises with this half of the parabola, with this half of the square. And when you take an inverse, so remember, an inverse is effectively taking numbers that are coming in on the left and mapping them to things that are down here on the bottom. When I take the inverse, mathematically, I need to make sure that I pick the right-hand side of the parabola and not the left-hand side of the parabola. That's what you're doing when you're choosing the plus or minus when you take your square roots. And so for this one here, I want to make sure that when I take my square root, that my range is going to be between -1 and 0, which is the range of this variable. I want to make sure my range is not between -2 and -1. So I go through the math, and then I end up getting stuck in this point where I say, okay, for my inverse, my random variate generator, my inverse CDF, it's either going to be -1 plus square root of R, or it's going to be -1 minus square root of R. Which one do I want? Well, again, I look at this and I say, well, -1 should be the bottom end of my range. And so I should be adding the -1. So that tells me that for this problem, I should pick the positive. So choosing the positive ensures I have the right range. If I would have chosen the negative, effectively, I would be choosing the wrong half of this parabola. And I would be saying that my range was stuck between -2 and -1, and that's not where this random variable is. Okay. Any questions about that? That is all the way up through your normal homeworks. So my next slides just kind of go fast, well, I guess fast rewind all the way back to the first lectures and just kind of pick up my highlight slides. But did that motivate any questions from you? So I got a private chat that asked me to go back a slide. Could you go back a slide on which X to use? And so the idea here is that I know this is a random variable that's stuck between -1 and 0. And I have inverted my CDF, and that gave me two options for the inverse CDF, either a plus here, or if I go to my annotation, it could have also been a minus. Just through the mathematics of square roots, it's either going to be a plus or a minus for this square root, but I got to pick one. So for this inverse transform generator, I know that this R number is going to be between 0 and 1. And so I want to make sure that if I plug in any number between 0 and 1 here, then the outcome here will be consistent with the range -1 to 0, which is down here, -1 to 0. That's the range that I want. And so the only way I can make this function with the plus or minus here, the only way I can make this function produce the right range from -1 to 0 is if I choose the plus there and not the minus. Okay. Did that help? Or are there more questions? Again, I got a private question to ask me to go back to that slide. Okay, great. So I'll clear those notes. Okay, so holler if you have any questions. We got about 13 minutes left in the class period here. If you have any other questions, feel free to post them in the discussion, send me an email, post them in the Slack. I'll look out for those things. The earlier the questions, the better. As we get closer and closer to the midterm, I'm probably frantically trying to finish the midterm. And of course, the TA can help with the questions as well. But if you want my help, the earlier the better. Okay, so remember what are models? The big thing, you know, they answer these what if questions. All models are wrong, but some are useful. So all of this kind of modeling philosophy, make sure you sort of feel comfortable with. The more concrete side of that is understand that, you know, we have static models like the Monte Carlo models, and we have dynamic models like our discrete event system simulations, where we're actually focusing on the model, not just at the end of the run, but as it runs all the way through the run. And we could have deterministic models or stochastic models. And so stochastic, you know, comes from that Greek word for guess or conjecture. We are, it's important to know that when we make a stochastic model, we are not saying that the system we are modeling is random. We are saying we have chosen to use randomness in our model to represent variation from the real system. But the real system doesn't have to be random. So understand that's what we mean by stochastic, because it's not, you know, you don't need a random real world to use randomness in the model to simulate it. You know, we talked about some motivations for why use computational models, strengths and weaknesses. You know, mental models capitalize on your experience that you've built up over a lifetime, but your mental models are typically better or worse at handling dynamical situations, and they're difficult to communicate to other people. And so these computational and mathematical models, they're much better at these dynamical situations and easier to communicate, but they don't count, they don't bring in all of the exceptions that your mind has accounted for over your experience. Different types of simulation models: discrete event system simulation, agent-based modeling, and system dynamics modeling we've talked about. So some basic familiarity with those. As I mentioned, all of the lingo: entities, attributes, resources, state variables, states, activities, delays, events, the event calendar, the future event list, another name for event calendar, and so on. Definitely know how to step through this table. You will see a table like this at least once on the midterm, and you'll either be asked to analyze it or to fill it in. And so know how to read these tables and know how to fill them in if there's empty spots. Know how to spot things that might be wrong, those sorts of things. So, and by the way, now that we're in Arena, I put up a little thing here. And if you notice, next to the play button, there's a little skip button in Arena, and that is the step button. And so in Arena, I claimed that behind the scenes, it has a future event list. And that's what moves the clock along step by step. Well, if you want to manually move through the steps of your simulation, instead of hitting play, you can hit that step button, and it will then go through the process that you went through manually in hand simulation. So just FYI, that's what that's out there. Yeah, know about activities, their durations. Know that activities can also be service durations, and know that delays are the things in between those durations. So activities versus delays. Any questions on that review stuff? Everybody feel pretty comfortable on the lingo? Okay. Um, Probability, yeah. So to definitely, review the probability stuff. So review probability mass functions, probability density functions, review the expected value variance, standard deviation, the formulas for those and what they are. Common distributions. So know that, I went through the kind of common ones that I said were important, so exponentials are good for waiting times, Weibel's good for failure times with non-constant failure rates. So we had a bunch of descriptions of the different reasons why you'd pick these fundamental models. Normal distributions are for additive processes. Poisson distributions are counts of events that happen during an interval, et cetera, et cetera. So know, those sorts of things. Know why we use these things. So this idea of input modeling, where we are selecting probabilistic models to model sources of variation from the real world, so that we can then generate simulations that have realistic variation on their outputs. And then we can study that variation, and we can see how to change the simulation to change the variation to offer operational questions. For those that need kind of a cheat sheet, these are the distributions that I think are most important for you to focus on. And know the basic parameters here. So, an Erlang K is the sum of exponentials. How many exponentials? K exponentials. And this lambda is inherited from the exponential. Again, the Weibel, if K is equal to 1, it is an exponential, but changing the shape variable of this makes it kind of like an exponential that tends to also fail very early or fail very late. Poisson, number of exponentially distributed events that occur in an interval. Binomial, negative binomial, and geometric. These are all related to the coin flip, which is the Bernoulli. Know that a random process, is a collection of an indexed collection of random variables. And our common example of that is the Poisson counting process, where the random variables that you're counting or you're collecting are counts. So they are Poisson variables that represent the count of events up to the particular time. So the index is a time, and the random variable indexed by that time is a Poisson random variable, which is discrete counts. So know that interrivals are exponentially distributed. So basically just become familiar with this kind of cheat sheet here. And this is kind of an expanded version of that. So these are kind of the one line description of what I think is important about these. So any questions about probability and random variables? Okay, got about 6 minutes left. Random variate generation, I already kind of beat you over the head with all of this stuff, so I'm not going to kind of dwell on this now, because if we do in the class on anything here, I think it'd probably be good to see things like the chi-squared test and the KS test and the runs test again. So I'm just kind of going to quickly jump ahead here, but if you'd like to ask any questions about random number or random variate generation, know that when I use the word random number, I mean a U01 number. When I use the term random variate, I mean a generic sample from a generic distribution. So random number means uniformly distributed between 0 and 1. That's a random number. A random variate is generic. It's a sample from any distribution. There was a private question. Are we going to need to know the PMF PDF for each distribution for calculations? No, I'm not going to ask you to. Well, I would say know about a uniform distribution. Be able to the shape-based distribution. So uniform and triangular. You may not need to know the formulas off the top of your head, but you should be able to, like if I drew a PDF for a uniform or triangular, you should be able to recognize that and then write the PDF for me. So those kind of like data-based or heuristic distributions, uniform and triangular, I would sort of be very comfortable with them. If things get a little crazy, like an exponential or whatever, I will give you the PDFs for that. I think it's good for you to know, to be able to write an exponential PDF and CDF, an exponential, but that's the farthest I would go. I don't think you should memorize what a normal looks like. Definitely not an Erlang K or a Weibel, but I would say if you want, just to be safe, uniform, triangular, and exponential, be comfortable with those PDFs and CDFs. And the others I'll give you if you need them. All right. Random number generation, be comfortable with the concept of a seed and what the seeds are for. LCG, we already talked about. Know that an autocorrelation test is a test that tests for predictability within a sequence. You know, how much does earlier numbers correlate with late numbers? But we use runs tests. And so the runs test, be sure to be able to, you can calculate a runs test. And so I've got examples here of the chi-squared test, which I'm not going to go through here because I feel like you probably should have had familiarity with that from the 380 and 385. In the last couple minutes here, I probably, unless somebody asks questions, we'll do a runs test. But make sure you also can do a KS test. So know that you need to sort these numbers and measure the distance to the kind of interval we expect the numbers to fall into. So be able to do that kind of KS test. And know that a KS test is for small sample sizes. And if the expected number that falls in the bin is less than 5, you cannot use a chi-squared test. And then runs tests. So maybe this is where we'll end here, but because this is probably the least familiar test to you. If you're given, know how to do a runs test. So this is a runs above and below the mean test. So give you a bunch of numbers. I will probably also give you the mean. So imagine calculating the mean of these numbers. Then you replace the numbers with whether they're above or below the mean. You're basically turning the numbers into coin flips. So if they're above the mean, they're heads. If they're below the mean, they're tails. So we'll call heads 1 and tails 0. And then from there, you can count how many heads you have, how many above the mean, how many tails you have, how many below the mean. And that's what NA and NB here. And then you can count the number of runs. And so a run is just the number of groups where they have the same outcome for a long string. So I've been highlighting runs here. And so this is them broken up. These are the 19 runs that are in this sequence of 30 outcomes. And then these formulas are ones that I definitely think you should probably put down on your formula sheet. So this is under the null hypothesis of independence, then this would be the average number of runs that you would get for an unfair coin with this heads to tails ratio. And this is the variance for that distribution. So for enough coin flips, it's normally distributed, and this is the mean and variance for that normal. And so with those, you can then calculate a z-score based on the number of runs that you actually observed. And that will give you a z-statistic that you can then use a z-test on. And so know that if I give you a level significance of 0.05, you go to the table, which I'll give you, you cut that 0.05 in half, and then you look up that, okay, so my critical value is 1.96. This particular value is under 1.96, so I fail to reject independence. I can't accept independence, but I can fail to reject it. All right. So I've got other slides here that you're free to go through just on inverse transform stuff, and being able to spot CDFs, PDFs, inverse CDFs by looking at graphs like these. That's another good thing to know how to do. But with that, I want to make sure that if you have questions, I'll stick around for a couple of minutes. But I want to make sure you guys get participation credit. So here's your attendance question today, which I'll also put in the chat. So chat has got the link. And the question for today is, what is the highest value a CDF can reach? So that is your question. What is the highest value a CDF can reach? So f of x is bounded by what value? And otherwise, that's all I've got for you in terms of review stuff. Are there any questions? If you don't have questions, you can feel free to pop off. That's all I've got today. There's an arena question from Lab 5. I'm happy to take that in just a second. Let me make sure that there's, and I will take that, and thank you for putting it in the chat. Are there any other questions that aren't related to the lab? You should know some basics about arena, but arena you won't really get a lot of arena questions till the final exam, but know some basics about arena. Any other questions about the midterm? All right, so a question from a lab: modified a model to include an inspection and assign a higher priority for things that have to be reworked. I'm correct in understanding that a low priority number effectively means a high priority, like they're the opposite. Yeah, there's a question about the lab. So for simplicity, so you can implement priority two different ways in arena. You can go into the queue settings in arena and you can say, take the highest attribute first, or you can go into the queue settings and say, take the lowest attribute first. Arbitrarily, in the kind of instructions that I gave you, I said, go and reconfigure the queue to take the lowest number first. And so the lowest attribute, in that case, you could assign like a -1 to that. So everybody gets an attribute of 0 by default. So if you assign a -1 to them, and then you say, take the lowest attribute first, the -1s will come out first. So it's your convention whether you view a high number as a low priority or not. Sometimes people view priority as like a ranking, like who's up first. And so if you're demoted in ranking, that means you're actually put ahead in the queue. So that's the reason why we have these two semantics. So you can say that high priority might mean lowest number or highest number. You just have to be consistent in your programming. And in the particular example I gave you, I just said, configure the queue as a lowest number first and figure out how to do it. But you could have also configured the queues for highest number first, and then you could assign them a higher number. And then the number sort of corresponds to a higher number as higher priority. But there's no solid convention on what, we have. It's actually pretty common for priority values to mean lower in priority value means actually higher in priority. Does that answer your question? Okay. Any other questions? Looks like we just got a small group of students left. In that case, good luck. Oh, if you wanted to save the report, is the only way to do it is to print a PDF or report in Crystal Reports. I haven't done a report in Crystal Reports for a while. Because Crystal Reports, that module is so old, I think the only way you could print it to PDF is if the machine that you're installed on has got like one of those PDF printer drivers installed. I would be surprised if Crystal Reports exports to PDF, because Crystal Reports is sort of like really old school. It's kind of like before PDFs were as standard as they are. I think if you look across the top in the really tiny, but the very top of the Crystal Reports, there is a little save button, but I would have to go back and check for sure. If you look in your book, though, it talks about this. But if you notice when you run an arena file, if you look in the folder that generates a bunch of junk, a bunch of output and all that, and there is a file in there, and I can't remember the text right now. It might be .out, but there is a text file in there that actually has all of the stuff that's in the arena in the report, but it's just in a text format. And so that's another great way to save those results. And then I also talk about other ways to save results. I've got a video on that posted on Canvas, but I don't know for sure if there's a way to actually save the Crystal report. But if you just want to save that data, look in the folder, and there is a file. I think it's .out, but I would need to double check to be sure. But there's a file that actually has a record that's generated by Arena even before Crystal Reports takes the data and processes it. And that text file may actually be nicer to use than the Crystal Reports. The downside of saving the Crystal Reports, it's got so many sheets that it may not be easy to save it into one large flat file. But I'll double check that for you. Okay, I can, so I'm gonna stop the recording now.